Alrighty, so we're gonna pick up with example 6. I think we finished 5 yesterday. Yes, we did. We talked about the acceleration. So we did finish 5. And hold on a second. I want to fix my screen sharing. Make sure I'm good here. Okay. All right. Hopefully everybody sees my desktop again and you see example 6. All right. Okay, here we go. Piece of paper. So in example 6, you have a spherical balloon being inflated at a constant rate of 5 cubic inches per minute. When the radius of the balloon is 4 inches, how fast is the surface area of the balloon changing? So first thing you want to do is, the best that you can, draw a picture. So it's a spherical balloon. Okay, there's my balloon. It's being inflated, so it's getting larger and larger and larger at a rate of 5 cubic inches per minute. So 5 cubic inches per minute is a rate of change. Let me move this down, huh? It's a rate of change and it's cubic inches per minute. So this is the rate of change of the volume, okay? So if we let V be volume, then dV dt is going to be the change in the volume, okay? Okay, so when the radius of the balloon is 4 inches, all right, so here's our R, and when that reaches 4 inches, how fast is the surface area of the balloon changing? So if you're looking for the change in the surface area, that means you're looking for d surface area dt. So we're going to have to take the derivative of a surface area formula in order to figure this out. So we need to know the surface area of a sphere. We probably need to know the volume of a sphere because they're giving us that, which means we got to plug this into the derivative of the volume. So let's see what we can do here. So I don't think I need this example hanging out here anymore because it looks like we got everything that we could possibly get from that example. So I'm just going to move this down. Okay, so let's start out with the volume of the sphere, okay? So volume of a sphere, anybody know what that formula is? Okie dokie. So it's 4/3 pi r cubed, okay? So 9 times out of 10, they're gonna give you your geometry formulas, but you know, sometimes it's good just to have them handy next to you. So if you Google like a geometry formula sheet from even your geometry SOL, you can just have all those formulas like all in one spot, okay? Okay, well anyway, so they're giving me the change in volume here. So I'm going to take the derivative of this volume formula so that way maybe I can plug this 5 in for when I take the derivative and figure out some stuff going on over here, okay? So when I take the derivative of volume, it's dV dt. Remember, we're doing all of our derivatives implicitly. Now, 4/3 pi, that's just a constant, okay? So you're not doing product rule or anything for this. You're just, you know, it's like power rule with some really nice constants. So the 3 is going to come out in front and it's going to cancel with this 3, right? So it's just going to be 4 pi r squared. And then implicitly, this is going to be dr dt. Okay? Now, you're going to plug in everything you possibly can. So what is this teaching you? More than just like a related rates problem, it's teaching you to like work with what you've got, okay? A lot of times when, you know, like in life, no matter what, you don't always have everything you need exactly like in the most convenient way. So you got to work with what you've got. So what did we have here? Well, we had a derivative for volume. So I'm going to have to work with that. So that's how I decided to use a volume formula. And since it was a derivative, I took the derivative. So we're going to put the 5 in for dv dt. 4 pi. Now, this r right here, that's coming from this r equals 4, okay? Because we can, where's my example there? I got to drag this back up. So this says here that the volume is changing at a constant rate. So that means like no matter what the radius is, the volume is still changing at 5 cubic inches per minute. So you can put the 4 in now because it's still going to be, the volume's still going to be changing at the same rate. So that's what allows me to do that. All right, so I'm putting the 4 in, squared dr dt. Well, this is kind of nice. I only have one unknown, so I could solve for dr dt, and hey, maybe I'll need it. I'm definitely going to need it over here for the surface area. So this is going to be 5 times, what's this, like 16 times 4, 64. So this is 64 pi dr dt, like that. And then you got to get the dr dt by itself, so divide. So this is like 5 over 64 pi. I'm just going to leave it like that. That is the most exact answer that I can give. So no sense in changing that into a decimal. I want to stay as exact as possible for as long as possible. Okay, so far so good. Everybody okay? Any questions? Okay, all right, cool. Anybody else? Okie doke. All right, so, okay, good. All right, so now this is just gonna hang out over here because there's gotta be a reason we were given this information. We're probably gonna have to use this. So now the final answer is the surface area. How fast is the surface area changing? Well, we need a surface area formula. Surface area of a sphere is actually one dimension down from the volume, right? Volume is 3D, surface area is 2D, two-dimensional. So actually the surface area is the first derivative of the volume. So the formula for surface area is 4 pi r squared, okay? So if you were to look that up on your SOL formula sheet, that's what you'd see right there, 4 pi r squared. So now we're going to take the derivative of that implicitly. So the derivative of surface area with respect to time is, remember 4 pi is just a constant. Bring the 2 out, so this is 8 pi r dr dt, like that. And now we want to know when the radius is 4, how fast is the surface area changing? So you're going to plug in what you've got to work with. So the surface area is going to be changing 8 pi times 4 times this lovely thing right here, which is actually going to make life a little bit nicer. Like that. So the pi's cancel. Let's see here. Some creative canceling. What can we do with this? 8 times 4 is 32, right? 32 over 64 is 1/2, right? So this comes out to be 5 halves. Okay, so it's actually better that we didn't try to get a decimal for this dr dt, because having the pi in there made this work out real nice and more accurate too. Now, this 5/2 represents a rate of change. It's a rate of change of surface area. So in this problem, surface area, our dimensions are in like inches and time is in minutes. So you're going to label this with inches squared, because surface area, per minute. Okay? So that's how quickly the surface area is changing when the radius is 4. Notice you get a positive answer, which should make sense, right? If you're blowing up a balloon, a spherical balloon, the volume's getting bigger and bigger and bigger. And what's that making the balloon do? It's making the balloon stretch, right? So therefore the surface area of the balloon should also be getting bigger. So that means that this should be positive. If you got a negative answer, then that means we got to go back and check something because it's not making sense. Okay, if you got a negative rate of change, that would mean that the surface area would be shrinking. Okay, any questions about that one? All right, not hearing anything or seeing anything. So I'm going to move on to example 7. All right, in example 7, we have 2 cars riding on 2 different roads that meet at a 90-degree angle. So remember drawing these pictures and stuff from trig where you have like the boat sailing out at like east, northeast, or whatever it was, and then you got another boat or a lighthouse or something somewhere. That's kind of what I feel like when I'm reading these. So let's try to draw a picture. 2 roads. There's the 2 roads. They meet at a 90-degree angle. Got it. 2 cars. Car A is 3 miles south of the intersection. Okay, here's the intersection. So 3 miles south of that would be down 3, and put a little dot right there. There's car A. Now that car is traveling north at 40 miles an hour. So this car is going this way at 40 miles per hour. Now, what's 40 miles per hour represent? It represents this change in distance, right? Every hour, we're going 40 miles closer up this road. So this, let's see, what do we want to do, you guys? How about, well, I guess I could have kept that there. That's not a big deal. If I call this little a, like this little distance right here, we'll call this little a, 3 miles. Then the 40 miles an hour, I'm going to move this. I put that in not a very good spot. I'm going to put it over here. The 40 miles per hour is going to be dA dt. Okay. Now here's the catch. This distance right here at some point is 3 miles. If car A is traveling north, then the distance between car A and the intersection is going to get smaller, okay, because the car is traveling north. So this dA dt is actually a negative 40. Okay, so let me explain that again, just in case you didn't catch it. So car A is right here. It's 3 miles away from the intersection. Right now, distance is all based on how far away the car is from the intersection. All right, that's how we're basing our judgment of the distance. Right now, it's 3 miles away. Since the car is traveling north, it's traveling toward the thing that we are measuring the distance from. That means that this distance is getting smaller and smaller and smaller. So therefore, this rate is negative, okay? Are we okay with that? We got that? Any questions about that? because notice they don't tell you to put negative in there. You have to like think about it, and you have to put your own negative in there with regard to where the car is placed and where it's going. Okay, I'll let that sit for a little bit. So then it says car B is 2 miles east of the intersection. Okay, so east of the intersection is out here. So we'll say 2 miles. Car B. Okay. And that car is traveling east, so it's continuing to go east at 50 miles an hour. All right, so this car is already 2 miles away from the intersection. We're basing all of our distance from how far away we are from the intersection. If it keeps going out to the east, that means this distance from the intersection is going to get longer, bigger, and bigger, and bigger. So if we call this side, I don't know, how about little b, then dB dt is the change in that distance, so that's 50. And since it's getting farther and farther away from the intersection, it'll be a positive 50 miles per hour, okay? All right, so now we got the picture. How fast is the distance between the two cars changing at this moment? So the distance between the two cars is this distance right here. That's how far away they are. Pretty soon this car is going to be out here and this car is going to be up here and the distance will be this, and pretty soon it'll be, you know, like that. So what you've got is this triangle that's changing shape as one car moves up and the other one moves over. Okay, so, and it's a 90-degree angle, which is also convenient. And we know some sides of a triangle with a 90-degree angle. So therefore, the only thing really we have to work with that's going to work beautifully is Pythagorean theorem. Okay, so I'm going to move this down. So we're going to go, we'll just call this C. So A squared plus B squared equals C squared. So we're really looking for how fast C is changing. So we are looking for dC dt in this problem. How quickly is this distance between the cars changing as this car moves north and this car moves east? So we're going to take the derivative implicitly. So 2a dA dt plus 2b dB dt equals, don't forget to do the derivative on the other side also, 2c dC dt, okay? Now, this one's different than the one we did yesterday. Yesterday's, the last example yesterday was talking about a ladder, and we did Pythagorean theorem for one of the parts, and C was the length of the ladder. And when we did the derivative over here, it went to 0 because the ladder stayed put, like it was a 10-foot ladder and it wasn't changing length at all. This is different. This distance is changing. So that's why we're going to continue with the derivative and it's not going to be 0 over here. Okay, so now we plug in everything that we know. So you got a 2, A for this was 3, dA dt is -40, plus 2 times B was 2, dB dt, positive 50, 2, C, don't know what C is. Can you figure out C for me? Somebody tell me what C would be if A is 3 and B is 2. What does C have to be?
The square root of 13.
Yep, good. Square root of 13, good. How'd you get that?
Pythagorean theorem.
Right, good. So 3 squared plus 2 squared equals c squared, and leave it like a radical. Okay, good. Now you got the dc dt, that's our only unknown, which is nice. And now we're just gonna kind of like try to simplify as best that we can. So 6 times negative 40 is negative 240, plus 2 times 2 is 4, 4 times 50 is 200. Check my math. 2 root 13 dc dt. I'm getting negative 40 equals 2 root 13 dc dt. Divide by 2 root 13, so negative 40 over 2 root 13, which is going to come out to be negative 20, right? Divide these over the square root of 13 dc dt. Okay. Okay. Now you can leave it like that. You don't have to rationalize the denominator. We should put a label on it though. So this would be negative 20 over the square root of 13. And this is a distance, and it's a rate of the distance per time. So this is going to be miles per hour. Or if you just want to put mph, that works too. Okay. So dc dt is changing at negative 20 over root 13 miles per hour. So since it's negative, you could say that distance is decreasing, okay? It's decreasing as one car goes north and the other car goes east. Okay. My drawing's not drawn to scale for sure, so. All right, so that's example number 7. Any questions on that? All right, let's look at example number 8. Okay, example 8, sand. Need a new piece of paper for this one. So sand is being poured onto a beach, creating a cone whose base diameter is always twice its height, always, no matter what, in any moment in time, the base diameter is always going to be twice the height. The sand is being poured at the rate of 20 cubic inches per second. When the height of the conical pile is 6 inches, how fast is the radius changing? How fast is the diameter changing? How fast is the height changing? And the angle, okay? So you have a pretty decent picture there. I'm gonna draw a picture. All right, so here's the sand pile, okay? So at the very beginning, they gave us some important information. Said the base diameter is always twice the height. So all the way across here is the base diameter. Okay. This is the height. That should be perpendicular. Okay. Maybe I just have my center drawn off a little bit. There we go. Okay, so the diameter, base diameter, is always 2 times the height. Okay. So diameter is a nice, like remember, diameter is all the way across, right? Diameter is it's a good measurement. It doesn't show up too many times in formulas, okay? The thing that shows up more often than a diameter in your geometry formulas is radius, right? So I would rather get this in terms of the radius because I know I'm going to have an R in one of my formulas, much more likely than a diameter. So we know that a diameter is 2 radii, right? So 2r actually equals 2h. So if 2r equals 2h, that means that when you divide these by 2, the radius is always going to equal the height. So by them telling you that the base diameter is always twice the height, they're really just telling you that the radius and the height are always going to be the same. So if I put an R down here, this is also going to be R every single time, okay, for this particular problem. All right, so that's good to know because that simplifies things a lot for us with regard to having multiple unknowns. So then it says that the sand is being poured at the rate of 20 cubic inches per second. So 20 cubic inches per second. Like if you write that down and look at those labels, cubic inches means you're talking about volume. So this is a rate of change of volume. So this is dV dt, okay? And it's being poured, so it's accumulating. The cone-shaped sand is getting bigger and bigger and bigger. The volume is growing, so it's a positive 20 cubic inches per second, okay? All right, so what else do they tell us here? When the height of the conical pile is 6 inches. So when this is 6, okay, that equals the height, which is also the radius. We want to figure out how fast is the radius changing. So part A is asking you for dr dt. Dr dt, that's what we're looking for. All right, well, work with what you've got, right? You've got a change in volume. So that means we need to work with a volume formula and take the derivative of it. So volume of a cone is 1/3 pi r squared h, okay? Pi r squared h is the formula for the volume of a cylinder. A cone is just 1/3 of that, okay? You can fit 3 cones in the cylinder. So, well, here's an interesting thing. We could start to take the derivative of this, but look what you'd have here, 2 unknowns, which means that you have to use product rule, and that would kind of be a pain in the neck, right? So let's use what we know up here. We know that H equals R. So really we could replace this with another R. Okay. Okay, so that means this is going to become 1/3 pi r cubed, like that. Now take the derivative. Not quite as bad. Don't have to do product rule. So dv dt equals, take the derivative, bring the 3 out in the front. That's going to cancel with this 3. So this will be pi r squared dr dt. Remember to do your derivatives implicitly. Okay, well, plug in everything you know. We know dv dt was up here, so that's 20. Pi r, they gave that to us. That was 6, right? Yeah, that's 6. So this is 6 squared. And then we're solving for dr dt, okay? Okay, so now it's just arithmetic. This is 36. You're going to divide by 36 pi on both sides. So 20 over 36 pi equals dr dt. So let's see, 4 goes into both of these, right? 20 divided by 4 is 5. 36 divided by 4 is 9. So 5 over 9 pi equals dr dt. Now, we need to label this. Our dimensions for this were inches and seconds. So this will be inches per second. Dr dt. And this is a positive answer. It's pretty tiny, but it's still positive. So it's still growing, okay? Which should make sense because if you're adding sand to a pile of sand, then the radius should continue to get bigger and bigger and bigger. Okay. Now let's look at part B. Part B is asking how fast is the diameter of the pile changing? Diameter. So the diameter, D equals, what's the relationship here? D is all the way across. Oops. D is all the way across. So D equals 2R, because this would be R, right? So if you want to find the rate at which the diameter is changing, maybe I should have made this like capital D. I don't know. Capital D for diameter. So this would be dd dt. That's going to be, the derivative of this is 2 dr dt. Okay. So then you're going to plug your dr dt in. So this would be 2 times 5 over 9 pi, which is going to become 10 over 9 pi. And this will be inches per second. Okay. Any questions about that? All right, part C. Part C is asking how fast is the height of the pile changing? So the height, well, we gathered from the very beginning of this problem that the height is going to be equal to the radius. So if h equals r, then the rate that the height is changing will be the derivative of h, and that's going to equal the derivative of r. If I take the derivative of both sides here, dh dt is going to equal dr dt. We know what dr dt is. We solved that already. That is 5 over 9 pi inches per second. Okay. All good so far? Any questions? Okay. All right, now the last part, which is fun. So now we're talking about an angle. As soon as you see that word, it's like, oh, trig, here we go. All right, so if the angle of repose, which they have labeled there for you, is defined to be the steepest angle at which dry, unconsolidated sediment is stable, what is the sand pile's angle of repose? And how fast is that changing? All right, well, actually, I'll come back up here. Here we are. So here's the angle of repose. Or if you want to, it could be this one over here. It doesn't matter. So you have a right triangle. Maybe I'll bring it out and draw it a little bit nicer. Okay. Okay, you have a right triangle. And this is the radius. Here's the angle. And then you have this height right here. I don't know what the hypotenuse is. I'm not sure what that is. We could probably figure it out. But right offhand here, that's not given information to me, so I don't know what that is. I'd have to do a little figuring to like get that. But I do know this information right here. H equals R. So if I put an R here, I can put an R here. And so therefore, that's an isosceles right triangle. And it's always going to be an isosceles right triangle because in this problem, we are locked into the diameter always being twice the height. Hence, the radius is going to equal the height. So what's that angle going to have to be if that's isosceles?
Is that 60?
Nope.
45.
Yeah, the other special right triangle. Yeah, so this angle right here is 45, and we always answer in radians, okay? In calculus, you always answer in radians. So what would 45 be in radians?
Pi over 4.
Yeah. So pi over 4 is going to be your angle of repose. Now, here's the next question, right? How fast is that changing?
It's not, right?
Yeah.
Right.
Constant.
Why isn't it changing?
There's no variable in that answer, so you can't take the derivative of it, or it'd be 0.
And the two sides are staying the same length. So
Yeah, good, right. So if this has to stay locked in as this ratio, then that angle is also locked in. Like this gets bigger, this has to get exactly the same size bigger. Like they can't change. The only way this angle is going to change is if one of these sides grows faster than the other one. If the bottom side grows faster, the angle gets smaller. If the side here, the height side grows faster than the bottom, then the angle gets bigger. But these are stuck in this ratio. So therefore, this angle is also stuck. So it's not changing. So how fast is it changing? It's not. D theta dt is 0. It's not changing. Okay. Good. Very good. That's usually like one that's, you know, a little challenging. Okay. Any questions before I move on to example number 9? Okie doke. All right, so let's see here. Let's see how well I can get number 9 on the, oh, that's not bad. They're fitting on here pretty nicely. That's pretty good. All right, so here we go. Example 9, a cherry flavored raspa snow cone, which I learned is a Texas, it's like a Texas thing. Like snow cones, obviously, we've had snow cones before, but like the raspa apparently is a Texas thing. So I'm assuming it's raspberry, I don't know. Snow cone is leaking from its paper cone at a rate of 2 cubic inches per minute. The paper cone's top radius is 2 inches and is 5 inches tall. When the depth of the melted cherry raspa mixture is 3 inches, part A, how fast is the radius of the raspa changing? Part B, how fast is the RASPA melt leaking into Nino Corpi's school clothes? And part C, if Nino Corpi has a small cylindrical cup with a 2-inch diameter beneath the leaking RASPA, at this moment, how fast is the height of the RASPA juice in the catch cup changing? So this is really good. This is a good one. Let's draw ourselves a picture. So we've got the cone upside down that's holding the RASPA. Oh, I guess it's not raspberry, right? Because it's cherry flavored. So I guess they just call it RASPA. I don't know. I learned this by watching Mr. Corpi's video one time. It's a Texas thing. Okay, anyway. So we know that the paper cone has a 2-inch, no, I'm sorry. The paper cone's top radius is 2 inches. So this R is 2. And we also know that the paper cone has a height of 5. Okay. All right, so in the beginning, it says that it's leaking from the cup, from the cone at 2 cubic inches per minute. So what we got here is like some leaks coming out of the cone. And this is leaking at a rate of 2 cubic inches per minute. So cubic inches, right away, volume, right? So this is a rate of change of volume. So that's a dV dt, but it's not being poured into the cone. It's leaking out of the cone. So these little drops are making this volume go down, right? You've had those snow cones before. It's like, once they start to leak, you're like, you better start sucking the juice out there because otherwise you're gonna be wearing it. So this is gonna be negative. Why? Because it's leaving the cone. The volume, this volume we're representing is gonna come from the volume of the cone. So if it's leaking out, the volume is gonna become less and less. So negative. You got to put your own negative sign on that. All right, got that. Got the picture drawn. When the depth of the mixture is 3 inches, so like when we get to about here, okay, depth is another way of just saying height. When the depth of the leaking out snow cone stuff is 3 inches, we want to know how fast is the radius changing, okay? So we want to know dr dt, okay? I'd really like to know how quickly this radius, the radius is getting smaller and smaller, right? Because it starts up at the top of the cone and works its way down and gets smaller and smaller. So I want to know how fast that radius is shrinking when we get down to just 3 inches of snow cone stuff in the cup. All right. Now, this is a different type of problem. It is using right triangles, but this is not a Pythagorean theorem question, okay? The reason that we're not going to do Pythagorean theorem with this is because we know absolutely no information about the hypotenuse, okay? And actually, well, I suppose you could argue that we could figure out this hypotenuse right here by doing Pythagorean theorem. But you're gonna end up, like if you do that, you're gonna end up, when you take the derivative of the Pythagorean theorem, you're gonna end up having a derivative of the hypotenuse that we don't know. Like we wouldn't know this side and we wouldn't know this side rate of change. So we don't want to do Pythagorean theorem for this. You want to set up something else that uses less variables. And so the only other thing that we could use would be similar triangles. Okay, so bring you back to some of your geometry again. If that's a right angle right here, this is also a right angle. This angle up here with the top of the cone and the slanty side of the cone is going to be the same as this angle right here. And so you can see there's like a little right triangle inside of a big right triangle. And both of those right triangles share this angle down here. Okay. So since all of their angles are equal, the big right triangle, this big one, is going to be similar to this one right here. What's that do for us? It means their sides are going to be in a set ratio. Okay. So we could say, like if I brought this out, you got big right triangle and you got little right triangle. Okay. That one could have been drawn. I'm just going to leave it. So they both have the same angle. They share this angle up here. I know for sure big right triangle is locked in at 5 because that's the height of the cone. That's not going anywhere. And I know big right triangle has a radius or a side of 2. I should have like radius equals 2. Put like a letter for one and a number for the other one and a height of 5. There we go. So now, little right triangle. That one's the one that's changing, right? Because as the snow cone mixture is leaking out of the cone, the radius is getting smaller and the height's getting smaller and it keeps changing. So I'm just gonna leave this R and H, okay? Now, I know that these are similar to each other, so they have to be in the same ratio. So 2 over 5, 2 over 5 has to equal R over H every single time because they're similar to each other. Or you could say 2 over R equals 5 over H. I mean, you can do this any way you want to, just as long as you go the same direction every time, okay? I just decided to do this side to this side equals this side to this side. Doesn't matter, okay? Now, when you cross multiply, this will be 2H equals 5R. That right there is some valuable information because we can use this to substitute in when we need things to like break down to one variable. So that was the key to start this problem out. And this always happens when you have a cone. So if you want to make a little note to yourself, similar triangles or use similar triangles with cones, okay? So instead of Pythagorean theorem, do the similar triangles. See how when we did this ratio, we only had 2 unknowns? If you tried to do Pythagorean theorem, you'd have 3 unknowns and it becomes too many things that like you don't have enough information for it. Okay, so that was nice, but we still got to figure out dr dt. Now, over here, you're like, well, there's an R right there. We could take the derivative of this, right? But look what happens when we take the derivative to this side. You would have a dH dt. I don't know what dH dt is. I don't have enough information. So I can't just take the derivative of this little equation over here. That's not going to work. So that's where our volume is going to help us out. The volume is there's some information there with that volume. So it's the volume of the cone. So we need that formula. V equals 1/3 pi r squared h. So see how you have two variables here? If you were to take the derivative of this right now, you would have to use product rule, which is fine. We can do that. But look what would happen. You'd end up with a dr dt, and you'd end up with a dh dt eventually, right? Because if we have to take the derivative with product rule, sooner or later, you're gonna have a dr dt and a dh dt in this. I don't know what dh dt is. They didn't give that to us. So you're gonna use this to help you out, okay? Wherever you see an h, you're gonna substitute in. Now, I didn't solve this for h. Let's actually get the h by itself, right? So divide by 2. So h actually equals 5/2 r. Okay, so wherever you see a h, put 5/2 r. So this will be r cubed. What else is going to be there? And a 5/2. Okay. And that is going to simplify. That could look a little bit nicer than that. Let's make that be 5 pi over 6 r cubed. So this 5/2 r turned into that h right there. So the 5/2 came over, another r came over, which made that r cubed. Okay. All right, now take the derivative of that. So the 3 comes out in front. You can cancel that a little bit with the 6. You can reduce that down. So this would be 5 pi over 2 r squared dr dt. Okay, now plug in what you know. We know that, well, we want to figure out dr dt when the height is 3. So I'm going to put a 3 in. Oh, I'm sorry. That was of height. Darn, I should have done the other thing, shouldn't I? Should we have substituted in for h? Or I'm sorry, yeah, for h instead of r. No, I guess we, I guess we'll have to plug it in and figure out what r ends up being. So do y'all see, like, we got the h, but I don't have an h down here. But I have an h over here, so I could use that. So I could say, take this 3 right here and put it in for this h. And that equals 5/2 r. See, I can't put that 3 in because it's, and I have an r, I need r instead, unless I labeled that wrong. Nope, I didn't. So we're gonna have to do a little extra work to get that r. Have I lost you? Are you okay? Questions? Okay, so we're plugging in over here because we have an r in our formula. So we're gonna multiply by 2/5 on both sides. So r equals 6/5. That's what you're going to put into your volume derivative because you can't put the 3 in. And you're also going to put the -2 in for the dv dt. So -2 equals 5 pi over 2 times 6/5 squared dr dt. All right, so -2 equals 5 pi over 2 times 36 over 25 dr dt. Simplify your arithmetic in whichever way you would like to. I'm going to cancel this 5 with the 25, make that 5. Cancel this 2 with the 36, make that 18. That's about as good as it's going to get, isn't it? All right, so I'm going to multiply by 5. That'll make this -10 over 18 pi. And that equals dr dt. And if I reduce it, it'd be -5 over 9 pi. And we are talking in inches per minute. So the radius is changing at a rate of -5 over 9 pi inches per minute. Your answer is negative because your radius is getting smaller, okay? Which makes sense because the stuff is leaking out the bottom of the cone. All right, that's part A. Any questions about that? So lots of substitution we did with that first part. Got to work with what you've got, right? And be really observant. Okay, part B. How fast is the RASPA melt leaking onto Nino Corpi's school clothes? So this one this takes thought, but it doesn't take any calculation, all right? So if it's leaking out of the cone at a rate of -2 cubic inches per minute, then it's leaking onto his shirt. His shirt is absorbing, the stain is growing at a +2 cubic inches per minute. So part B is just realizing that the same rate of change for the volume coming out of the cone, which is a negative, would become a positive rate of change as it goes onto his shirt. So silly, but actually an important conceptual understanding. So this would become +2 cubic inches per minute. All right, part C. That was it for part B, that was it. Part C, if Nino Corpi has a small cylindrical cup with a 2-inch diameter beneath the leaking RASPA, at this moment, how fast is the height of the RASPA juice in the catch cup changing? Okay, so try to salvage my picture a little bit here. So we have the cone with the stuff leaking out the bottom. So then he has now a cylindrical cup underneath the cone that's catching everything that drips out. It's got a 2-inch diameter. I did not make this, like, I need to clean this up just a little bit here. Let's make it look like this. Okay, 2-inch diameter. So all the way across this 2, that means that the radius has to be 1, right? The stuff's leaking into it. All right, so the radius is 1. Now it's a cylinder, right? So think about this. When you're filling up a cylinder with liquid, as you fill the cylinder up, with more and more liquid, okay, what's happening to the radius? As you fill a cylinder up with liquid, the liquid is rising, okay? What's happening to, like the radius on the cone is changing, right? This radius is different from this radius, is different from this radius, is different from this radius. When you fill up a cylinder, what happens to the radius?
Diddly squat. Nothing happens.
Yeah, stays the same, right? Good. So keep that in mind. So they're asking us, how fast is the height changing? So we're looking for, so like this is leaking out, right? And then it's forming like a little bit here, and then it gets higher and higher. So how fast is the height changing? Okay. Well, we know that the amount of snow cone stuff leaking into the cone is a change in volume. Now, this is another thing we need to think about. This is not leaking out of something for this problem. This is now leaking into something. It's like leaking into the catch cup. So the change in volume of this cup is positive now. So it's a positive 2 cubic inches per minute because it's increasing. We also know that the radius is 1. So if we use the volume formula for a cylinder, we can take the derivative of it and solve for dH dt. So once again, let me talk about what we're doing. You have snow cone stuff leaking into a catch cup. And so therefore its rate of change of volume needs to be positive. It's not negative anymore, it's positive. If we know the volume of a cylinder, we can take the derivative of that formula and solve for the change in height, dH dt. So volume of a cylinder is pi r squared h. So we talked about how this has got 2 unknowns, right? But we know what the radius is, and we know that the radius is always going to be that number because in a cylinder, the radius stays the same no matter what, no matter where you are on the cylinder, the radius stays the same. So we could replace this radius with 1 because it's always going to be 1. It's not going to change. So your volume for this particular cylinder is just going to be pi times h. Now take the derivative of it. So the derivative of v is dv dt. And then the derivative of pi h is pi dH dt. We're looking for dH dt. That's good. Put the 2 in for the dv dt and solve. So this will be 2 over pi dH dt. This is representing the height, the change in height. So this is going to have a label of inches per minute. Okay. 2 over pi, whatever that number comes out to be, it's something less than 1, but it's positive, and that's a good sign. Like that means we have a reasonable answer, because if you have a positive rate of change, then that means that your height should be increasing. And that should make sense in this problem. The more stuff that leaks into that catch cup, the higher the height is going to be. All right. Any questions on that one? Okay, so let's do number 10. We have like 10 minutes left of class. I'm hoping I can get number 10 done in the last 10 minutes. And then if I need to, I'll make a video of number 11. Okay, so example 10 from 1984. Oh my goodness, the good old days. I was like, gosh, I was 8 years old in 1984. What a fun time that was. All right, so long time ago, holy cow. The volume V of a cone is increasing at the rate of 28 pi cubic inches per second. All right, cone, volume of a cone, dV dt, increasing, positive, 28 pi cubic inches per second. All right, so here's the radius. Here's the height. All right. At the instant when the radius on the cone is 3 inches, volume is 12 pi cubic inches. And the radius at that instant is also increasing. So the radius is increasing at 1/2 inches per second, 1/2 inches per second. So that is your dr dt. Take a look at that and see if you follow that. Okay. Okay. So part A. At the instant when the radius of the cone is 3 inches, what is the rate of change of the area of the base? Okay. I drew my cone upside down, didn't I? I guess it doesn't matter. All right, so you are looking for the rate of change of the area. Rate of change of area. So like dA dt. Well, we need to take the derivative of the area of the base. Well, the base is a circle, so the area is going to be pi r squared. So when you take the derivative of that, that'll be dA dt. Bring the 2 out in the front. 2 pi r dr dt. I know that r is 3. I know dr dt is 1/2. So I can just plug all that in. So 2 times pi times 3 times 1/2. And then simplify. So the 2's are going to cancel. You're left with 3 pi. And this is the change in area with respect to time. So this is 3 pi inches squared, because it's area, per second. Okay. Okay, that's not too bad. Part B. At the instant when the radius of the cone is 3 inches, what is the rate of change of its height? All right, so we need a dH dt. What is the height going to be? Well, I don't have anything with a H in it. Like they're not giving me any, I got volume, I got rate of change of volume, I got R, I got dr dt. I don't have dH dt. All right. So we could try to use volume. What if we do that? So volume, well, it's a cone. So volume is 1/3 pi r squared h. I don't know what h is or dH dt. I guess what we'll have to do is we're gonna have to use this r equals 3 and this 12 pi. We're gonna have to use that to figure out what h is. And then we should be able to have enough information, I think. So if I know that the volume is 12 pi when the radius is 3, I can plug that into my volume formula and then get the h by itself. Because if I just keep this like this and I take the derivative of it, I'm gonna have too many unknowns. So I gotta figure out what this h is. Okay, so this is 9. 9 divided by 3 is 3. So if I divide both sides by 3 pi, I get that h is 4. Okay. So I know h is 4, I know r is 3, I know that dr dt is 1/2. Oh, and I know dv dt is 28 pi. Okay, I think I've got everything I need so that I can do dH dt now. Okay? Okay. Oops, did not mean to do that. All right, so now we're gonna do volume again, 1/3 pi r squared h. This is gonna be my u and h is gonna be my v. I got a do product rule for this. So dv dt equals, this is just a constant right here, all this just constant. In fact, I'm just gonna write it as pi thirds. So this, you take the derivative of all of this, so bring the 2 out in front. So it'll be 2 pi over 3 r to the first power dr dt times h. So this was u prime times v plus v prime, which is dH dt times u. So this will be pi over 3 r squared. It's a lot of little things in there to keep track of. Okay, now you're gonna plug all this information over here into this. So 28 pi equals 2 times pi over 3 times 3 times 1/2 times 4, goodness, plus dH dt pi over 3 times 3 squared. Okay, bell's gonna ring here in like a minute. Okay, so this goes, those 3's go, the 2's go. This becomes 4 pi plus, this is like 9 divided by 3, which is 3 pi. So this would be 3 pi dH dt. Okay. So now you're gonna get the dH dt by itself. So subtract 4 pi from both sides. That's gonna make this 24 pi equals 3 pi dH dt. And then divide by 3 pi on both sides. So the pi's go. 24 divided by 3 is 8. So this all came out to be a nice whole number. How about that? So the label on that, this is the change in height. And that is inches, yeah, per second. Okay. DHDT is inches per second. Okay. Part C, real quick, if I can sneak it in here. Part C is, at the instant when the radius of the cone is 3 inches, what is the instantaneous rate of change of the area of its base with respect to its height? So this is kind of weird, kind of different. Let me just reduce this down. So with respect to its height, not with respect to time, with respect to h. So this is so bizarre because like you would never like actually calculate this. Well, maybe you would in a, I don't know if you would ever do this in real life. Would we ever? I'm not going to go down that road. Anyway, so dA, dH. That's what you're looking for, dA, dH. So if you are calculating dA, dH, watch what you can do here. You can take your answer from dA, dt, and you can divide it by your answer from dH, dt. Okay, remember these derivatives that are written as fractions, like change in y over change in x, they're just fractions. So we can treat them like fractions. And so if I have dA over dt, which we did figure out, and I have dH over dt, which we just figured out, and I divide them, I can cancel out these dt's. Or you could just do keep, flip, change, and the dt's will cancel out that way. And you'll be left with dA, dH. So what was our answer for dA over dt? It was 3 pi. So we had 3 pi for that answer. And my answer for dH dt, we just figured out, was 8, right? Yeah, that was just 8. So you put that in the bottom. And so this is your instantaneous rate of change, your derivative, of the area of the base with respect to its height. Now, the label on that is just like atrocious. So this would be inches squared per inch. Like that's why it's so like, I don't know if we'd ever, I'm sure there's some engineer out there that's doing stuff like this to compare things, but it's kind of bizarre. So inches squared per inch, which kind of just simplifies down to just inches. So the ratio would be 3 pi over 8 inches. So the rate of change actually is just a linear measurement. Get that out of the way. Okay? Okay, so at this moment, I am going to stop the recording because I don't know if